Determine the forces in the members of the space truss. State whether they are in tension or compression. Looking at this truss, we know that ABC is a equilateral triangle, and we can find our angle at A, B, and C. So for our angle for CAB is simply going to be cos theta which I'm going to name this angle as cos theta. And another thing we need to find before we solve for the angle theta is our height at this point here, and I'm going to name it B prime. So it's going to be just 1 meter because it's equilateral triangle. That means half the length of AB. It's going to be 1/2. This comes up to be 60-degree angle, and our angle beta is simply going to be 30 degrees. Or if you're looking at the whole angle, then it's going to be 60 degrees. Now let's begin solving. And before we begin solving for the forces in member, we need to solve for our external reaction forces. So the only external reaction force that is going to act along this truss for the calculation of our required members is CZ, and by inspection we know it's going to be 5 kilonewton. Now we can start solving from the joint D. Let's draw the free body diagram for D. So at D we're going to have external reaction force of 3 kilonewton, and this is projecting along y-axis. Then we have external reaction force of 5 kilonewton, and it's projecting along z-axis. Then we have our unknown force from member CD, and it's projecting along y-axis as well. Then we have our unknown AD, and it's projecting along all the axis, and so is BD. And because this truss is symmetrical, we know that our AD and BD are similar. Now we can start solving, and we can start from our z-axis by summing the forces in z direction. We're going to have negative 5 kilonewton, and then we're going to have positive 2 times, and that's because we know that AD and BD are going to be same, and so we're going to take one of the two, AD or BD, and then times its z component, which is simply going to be, first we need to find our, I'm going to name this CB prime. So the CB prime length is going to be, we can use sine 60 with the hypotenuse, and we'll get root 3 as our solution for the length of CB prime. So it's going to be the z component of the AD, and BD is going to be 1.73 divided by square root of 3, and squaring it gives us 3. Then we're going to have our x component, which is simply 1, and then our y component, which is going to be 4, all equals to 0. Solving for AD, we get our solution as 4.08. kilonewton. And since we received or got our solution in positive, this means we assumed our vector direction to be correct, and this tells us that our AD and BD, both of them are in compression. Now we can sum the forces in y direction and get our solution for force CD. We're going to have negative force CD, positive 3 kilonewton, and then we're going to have positive 2 times either of the forces, AD or BD, times their y component, which is 2 divided by square root of 3 plus 1 plus 4, which is just square root of 8. And it can further be simplified into 2 root 2, all equals to 0. Solving for force CD, we get our solution as 8.770 kilonewton. And since our solution is in positive, this means our assumed vector direction is correct, and this tells us this member is in tension. Now we can proceed to our joint C. At joint C, we have force CA acting along x-axis and projecting along y and z. Pardon me, x and z. And then we have our other force CB, and it's projecting along x and z. Then we have force CD, which we have found already, and it's 8.770 kilonewton, and it's projecting along y-axis. Okay, now to solve this problem. Oh, and another thing we missed, z, axis reaction force. So, and this is 5 kilonewton. Okay, now that we have everything, we can start solving in z direction. So that means we have to use some of the forces in z-axis direction. So we're going to have positive 5 kilonewton. And then because there is another symmetry here, CA and CB are both symmetrical. I'll write it here so that we don't forget it. So this means you're going to have negative 2 times either CA or CB times their z-axis component, which in this case is going to be square root of 3, which is 1.73, divided by square root of 3 squared plus 1, all equals to 0. Solving for force C, we get a solution as positive 2.887 kilonewton. And since it's in positive, this means vector direction is correct, and that means both of these are in tension, force CA and force CB. Now let's see what we have found so far. We have found CD, we have found DA, we have found DB, we have found CA, we have found our CB as well, and we're left with just the member AB. Alright, to solve for member AB, we will need to draw our free body diagram for member A. For member A, we're going to have our reaction from or force from member CA, and it's projecting along X and Z. Then we have our unknown force member A, B, and it's projecting along just the x-axis. And finally we have our known force in member AD, which we found to be 4.082 kilonewton, and it's projecting along X, Y, and Z. And our force CA we found to be 2.887 kilonewton. Now to solve for this problem, just need to sum the forces in the x direction and get our equilibrium equation. So we're going to have positive 2.887 kilonewton and its x component, which in this case is going to be 1 over 2. Then we're going to have negative 4.082 kilonewton and its x component, which is going to be 1 over 2 root 2. And then finally we have our positive force AB, all equals to 0. Solving for AB, we get our solution as 0.0025 kilonewton, which is equivalent to 0 kilonewton. And with that,